Sir Isaac Newton signing off. Cheerio.
Ah, gravity. That force we feel but do not see. Anything that has mass has gravity. Though quite small compared to the massive Earth, you and I, even a grain of sand has some gravity. The force of gravity between two objects depends on two things: their masses, or weight, and their distance from each other.
If I stand on the ground here, there's a gravitational force that gives my mass a certain weight. If I climb up this tree, I've increased my distance from the Earth. Up here, the force of gravity is less, meaning I would actually weigh less. A teeny tiny fraction of 1% less, but still less. If you want to take off some weight, get yourself farther from the Earth's surface. You can do it by standing up. So, stand up. Yes, I mean you nice folks in the planetarium audience out there. Stand up. All of you, come on, stand up. Good job. There, you all weigh less. You've increased your distance from the Earth's center. Like me up in the tree here. Feels good, doesn't it? Okay, you can all sit back down. Thank you.
We need to understand gravity if we hope to understand the stars and how they shine. Stars, including our own sun, are tremendously massive, much more so than our beautiful blue Earth. If you could miraculously stand on the sun, the force of gravity would cause a 100-pound person to weigh almost 3,000 pounds. A star's force of gravity is gargantuan.
It's easy to explain how a ball of gas as big as the sun, or any other star, radiates as much light as it does. Compress a gas and it heats. Heat a gas and it wants to expand. But gravity counteracts the expansion.
Such a massive ball of hydrogen gas has so much weight or mass, compressing upon itself, that the pressures and temperatures build and build until the core gets so hot that hydrogen fuses to helium, a nuclear reaction which releases vast amounts of energy, which counteracts the gravitational contraction. The giant gas ball stabilizes, and a star is born. Its light radiates out in all directions into the blackness of space.
Never, by any means, shall we be able to study the chemical composition of the stars.
This 19th century prophecy was reasonable for its day, but it turned out to be very wrong. We do know what stars are made of. They are huge balls made almost entirely of intensely hot hydrogen and helium gas. And we've grasped this fact without ever having traveled to the stars. The answers were found not by looking over the rainbow, but into the rainbow. The rainbow in astronomy is called the spectrum. This visible energy is only a tiny part of a much wider electromagnetic spectrum, most of which our eyes cannot see. The lower energy waves are found in the radio and infrared regions, while the higher energy waves are found in the ultraviolet, X-ray, and gamma regions. In 1814, the German lens maker Joseph von Fraunhofer used a spectroscope, which has a prism that splits a star's light into its component colors, its spectrum. What the stargazer saw amazed him. thin black lines were embedded within the solar spectrum. Soon after, to his astonishment, he found that the distant stars also had the same skinny black lines in their spectra. Fraunhofer helped prove that stars were faraway suns. But what were those tiny black lines?
They are absorption lines. Here's how they work. As light radiates outward from the center of a star, chemical elements in the star's outer atmosphere absorb specific wavelengths of the star's light. For example, here is the picture of a continuous spectrum from an incandescent light source like the sun. Now hold up your index finger against the red part of the spectrum. Your finger represents the darkest line of the element hydrogen in the cooler outer layers of the sun. This time, place 2 fingers of your left hand close together over the yellow-orange part of the spectrum. Different elements in the sun's outer layers absorb different parts of the solar spectrum. Now your 2 fingers represent the element sodium. These amazing absorption lines tell us the chemical secrets of the stars. Okay, you can rest your arms now. Thank you.
Pardon me, everyone. Can I stop your show for a few moments? I noticed a few other stargazers from long ago popping in, so I figured it'd be okay. Hi, I'm astronomer Cecilia Payne-Kapashkin. In 1925, I discovered one of the biggest chemical secrets of the universe. I was the first to discover that the sun and the stars were made mostly of hydrogen. Oh, people knew hydrogen was there before. But by studying those absorption lines very closely, I learned that when it comes to the sun and all the stars, hydrogen dominates. To me, the scientist's reward has always been the emotional thrill of being the first person in history of the world to see or understand something. Nothing can compare with that experience.
Each star's spectra peaks at a different color. The brightness, together with the thickness and darkness of these celestial fingerprints, tell us the star's chemistries and temperatures, and ultimately, how they will end their fantastically long lives. Scientists draw a line horizontally, representing stellar temperatures from hot on the left to cold on the right. The blue stars are actually hotter than the red stars, so they are found on the left and the red stars on the right. A star's position on this line, based on its detailed spectra, is referred to by its spectral class, which is given a letter.
Give me an O. Oh, come on, humor me a little bit.
O.
Give me a B.
B.
Give me an A.
A.
Give me an F.
F.
Give me a G.
G.
Give me a K.
K.
Give me an M.
M.
What does it spell?
Okay, the spectral letters don't spell anything. They're a result of new stellar findings and quirky history. However, nothing characterizes a star quite so much as its spectral class letter. It is the first thing about a star that any astronomer wants to know. What is the star's letter, or temperature? Stars emit different amounts of radiation into space, generally depending on their size and temperature. The total output of radiation emitted by a star is called its luminosity. If we draw a line vertically, we can place stars along this line from bottom to top in order, from stars least luminous to those most luminous. These 2 lines form the HR diagram, named for 2 astronomers, Hertzsprung and Russell. To explain the scientific significance of the HR diagram, we would like to invite Dr. Kaler himself into the planetarium.
Well, hello there. May I join in? Stars happen to be one of my favorite subjects. Could I borrow that pointer for a moment? Thanks. You know, I made my own planetarium when I was 14. Still got the thing. Of course, it's not as nice as this place, Figuring out a star's personality by plotting it on the HR diagram is fascinating. We found stars that both dwarf the sun and that are dwarfed by the sun. Stars are not created equal. Our eyes give us clues right away. Take a look at this star in the foot of the great hunter, Orion. It is a beautiful blue-white supergiant star named Rigel, one of my favorites. Since it's blue, it's hot. Its spectral lines tell us that it is a giant, quite luminous, because it is both hot and has a large surface area. So where should we place it on the HR diagram? Here? Over here? If you thought here, near the upper left, you were correct. Hot goes on the left, and very luminous means near the top, so Rigel goes here. Now look at this star, Betelgeuse, in the shoulder of Orion. It is also a supergiant star and very luminous, but it's red, meaning its temperature is cool for a star. Where should we place Betelgeuse on the HR diagram? If you chose near the upper right corner, you're correct again. Our sun's radiant energy peaks in the yellow-green part of the spectrum. Its spectral class, or temperature, tells us that it is a G star. The sun is also a fairly small star, so its luminosity places it here, in the middle of the HR diagram.
If you place the stars on the diagram one by one, you'll notice they're not spread randomly.